the properties of logarithms. So, we're going to start by looking at an exponential property that you hopefully already know. We have a to the m times a to the n. Okay, and hopefully you know exponentially that is equivalent to a to the m plus n. Okay, well, let's look at the following two situations where we have the log base b of x equals m and the log base b of y equals n. Okay, if I were to convert both of these to exponentials, the first one would look like b to the m equals x. The second one would look like b to the n equals y. Okay, now what would happen if I multiplied b to the m times b to the n? That'd be the same thing as multiplying x times y. Okay, well, what if I take this and I use this exponential property we used above and simplify it some? So now this is b to the m plus n equals x times y. Now what if I try to convert this back to a logarithmic function? It would convert to log base b of x times y equals m plus n, right? All right, well, what's m plus n? Let's see. Well, log base b of x times y equals, we said m is technically the log base b of x, and then n is technically the log base b of y. So we now see that we have an equivalency here, that the log base b of x times y is the same thing as the log base b of x plus the log base b of y. Okay, let's go through some more properties. So it says take x, y, b all positive, and b not equal to 1. The log base b of x times y, we just discovered that one, is equivalent to the log base b of x plus the log base b of y. Now let's look at this one, the log base b of x over y. That converts to be the log base b of x minus the log base b of y. Now, how about the situation here? The log base b of x to the nth power. Well, it turns out that converts to be m times the log base b of x. And the log base b of b to the nth power. Okay, let's solve this one. Okay, let's just try to solve and figure out what it might be equal. What if I converted this into an exponential form? The exponential form of this would be b to the something equals b to the nth power. So what does that something have to be here? This question mark. Well, it has to be m. There's no other choice. So log base b of b to the m is just m. It's almost like the log base b of b just cancels itself out. How about this one? Let's do the same thing here. Now here I have b raised to the log base b of m. What if I converted that one to a logarithmic? Well, that would be the log base b of something equals the log base b of m. So that something would once again have to be an m. Okay. So it's almost like the b and the log base b cancel out. Now let's look at this example. It says we want to write the sum or the difference without using exponents. So here I have log base 3 of 6x squared y to the third power. We basically want to split this up, write it as a sum or difference of logarithms with no exponents. First thing I'm going to do is write it as a sum or difference, and then we'll pull the exponents forward. So I'll split this into a log base 3 of 6 plus a log base 3 of x squared plus a log base 3 of y to the third. Now I need to handle my exponents. My first term didn't have an exponent, so I can leave it alone. That's the log base 3 of 6. It also doesn't simplify to anything nice and neat, so I'm just going to leave it like that. And I'm going to pull the squared forward, so it'll be 2 log base 3 of x. Now I'm going to pull the cube on the y forward, so it'll be 3 log base 3 of y. Now I've written this as the sum and difference of logarithms with no exponents. Let's look at this other one. Here we have the log of x to the 7th, y to the 5th, all over z to the 4th. Well, this will be the log of x to the 7th plus the log of y to the 5th minus the log of z to the 4th, because the z to the 4th is in the denominator. I need to take care of these exponents, pull them to the front, so I have 7 log x plus 5 log y minus 4 log z. And it's that simple. All right, this one, we have a natural log. Same thing, we're writing it without using exponents. So this will be the natural log of x to the 5th minus the natural log of y squared minus the natural log of z to the 8th, because those are both in the denominator. I have to subtract both of them. Then I just need to pull the exponents to the front. This will be 5 natural log x minus 2 natural log y minus 8 natural log z. It's that simple. Part B says the log base 2 of w to the 2/3 power times x to the 4th divided by y to the 3rd power z. Okay, well, this would be the log base 2 of w to the 2/3 power plus the log base 2 of x to the 4th minus the log base 2 of y to the 3rd power minus the log base 2 of z. Now we still have to get rid of these exponents, so I have to bring them to the front. So, oops. First one will be 2/3 log base 2 of w plus 4 log base 2 of x minus 3 log base 2 of y minus the log base 2 of z. So, written them as a sum or a difference without using any exponents. All right, now how about this one? It's a little bit bigger one here. We have the natural log of the 5th root of x to the 3rd over y squared z. Okay. Now, in case you don't know, this is equivalent the 5th root is equivalent to raising it to an exponent of 1/5. Okay. What I'm going to do is go ahead and bring that 1/5 out front. So it'll be 1/5 times the natural log of x to the 3rd over y squared z. Okay. Now, what I'm going to do is I'm going to leave the 1/5 in the front, and then I'm going to start breaking this up into different natural logarithms. So it'll be the natural log of x to the 3rd minus the natural log of y squared minus the natural log of z. Then I can bring those exponents forward, still leaving the 1/5 out front. It'll be 3 natural log of x minus 2 natural log of y minus the natural log of z. Okay, and if I want to simplify this a little bit further, I can write it as 3/5 natural log of x minus 2/5 natural log of y minus 1/5 natural log of z. And I have now written it as a sum or difference without any exponents. Now let's look at this question. It says given log base b of 2 equals 0.63 and log base b of 5 equals 1.46. We want to evaluate the log base b of 40. Okay. What I want to do is use the 2 and the 5. Okay, I want to get it in terms of 2 and 5 here so that I can use those values that I know to kind of substitute in here. Okay, I'm not really looking to solve for b. All right, so how can I break 40 up so that I get 2's and 5's? Well, I do know that 5 will go into 40, so I could break it up into log base b of, say, 5 times 8, right? Okay, that gets me a 5, and then if I look at the 8, how do I get an 8 from a 2? Technically, an 8 is a 2 to the third power, so I could write it as the log base b of 5 times 2 to the third power. Okay. Then I can use my properties where I could break it up into single logarithms. So it would look something like the log base b of 5 plus the log base b of 2 to the third power. And then I can use my property that says, hey, I can pull that exponent to the front. And now I can use my substitution property here to substitute in 1.46 for that log base b of 5. I'm going to substitute in the 0.63 for the log base b of 2. And take a second, pull out your calculator. And all you have to do now is do 1.46 plus 3 times 0.63. You should get 3.35. Fairly certain that's correct. Indeed. All right, now let's look at the second one. Here we have log base b of 25 times b to the third. Okay, let's go ahead and split this one up. It'll look like the log base b of 25 plus the log base b of b to the third power. Now I still want to get it in terms, the one with the number in it, I want to get it in terms of 2's and 5's. 25 is 5 squared, so I should be able to pull that off. I'm going to go ahead and write this as the log base b of 5 squared instead of 25. But what do I know about the second term here? The log base b of b to the third. I have a property that says that that should simplify down to 3. Okay. Well, then what I could do, I could pull the squared forward. So I'll have 2 log base b of 5 plus 3. And I know the log base b of 5 is 1.46. So it's going to give me 2 times 1.46 plus 3. And if I pull up my calculator, 2 times 1.46 plus 3, I get 5.92. And I'm good to go. All right, another style example. It says given log base b of 2 equals 0.63 and log base b of 5 equals 1.46. We want to evaluate log base b of 1/10. Okay, well, let's rewrite this as the log base b of 1 minus the log base b of 10. How about that? Now, what is the log base b of 1 equal? B to the what power equals 1? How about 0? It does turn out that that first part will be a 0. but I still have to get a 5 and a 2 out of the second part. Well, how can I combine a 5 and a 2 to get a 10? Could just multiply them, right? So here I have minus log base b of 5 times 2, which I can then split up into minus the log base b of 5 minus the log base b of 2. Okay, because I have to keep that minus with both terms, even though they're technically added because they're multiplied. Now this gives us minus 1.46 so minus 1.46 minus 0.63. Okay, so if I take those and I subtract them, we get minus 2.09. Okay, well, how about this one? Log base b of b over 50. All right, we're going to break that into the log base b of b minus the log base b of 50. Well, what do we know about the log base b of b? That should equal 1. And then I need to split the log base b of 50 into 5s and 2s. Okay, so what if I split it into the log base b of 2 times 25? Okay, because 25 is 5 squared. This is going to give me 1 minus the log, base b of 2 times 5 squared, which is the same thing as 1 minus the log base b of 2 minus the log base b of 5 squared, which is the same thing as 1 minus the log base b of 2 minus 2 log base b of 5. Now I'm going to go ahead and do my substitution. It'll be 1 minus 0.63 minus 2 times 1.46. Now all you have to do is take your calculator, type that in. 1 minus 0.63 minus 2 times 1.46. You get negative 2.55. And you're done. Now we've converted from a single logarithm to a multiple of logarithms where we've added or subtracted. Now we kind of want to do a reverse, right? We want to take these expanded logarithms and turn them all into a single logarithm. So here we have 3 log x minus 2 log y minus 5 log z plus 7 log w. Okay, first thing I'm going to do is put the exponents back in place. So I'm going to pull the 3 back on the x, I'm going to pull the 2 back on the y, the 5 back on the z, and the 7 back on the w. So it'll look like the log of x to the third minus the log of y squared minus the log of z to the fifth plus the log of w to the seventh. Now, all the positive terms are going to be in the numerator. All the terms with the negative out front, the y and the z, are going to be in the denominator. So when I go to combine them into this single logarithm, it's going to look like the log of x to the third, w to the seventh, over y squared, z to the fifth. That's it. All right, let's look at this one. Here I have the natural log of x plus 2 plus 3 natural log x. I need to put the 3 back on the x. Okay, so it's going to look like the natural log of x plus 2 plus the natural log of x to the third power. Now they're added, so they're going to be multiplied. So it's going to look like the natural log of x plus 2 times x to the third power, which if you wanted to simplify would look like the natural log of x to the fourth power plus 2x to the third power. Just like that. That completes the properties of logarithms lecture. If you have any questions, send me an email, let me know. I will see y'all next time.